what is the temperature difference between the hot cup and the ceramics. So we have a copper constant differential thermocouple, which will give whatever is the temperature difference multiplied by 40 microvolts per every degree. So if the temperature difference is 20 degrees, it will give 800 microvolts. This is amplified 100 times so that you will get 800 into 100 is 80,000 microvolts or 80 millivolts. So the differential amplifier is used in all experiments in which we need to measure temperature difference using a thermocouple. The constant current source is used in all experiments like Stephen's constant, that you have thermal conductivity of copper and perspex, where you produce a known heat and find what is the temperature difference. Or in calibrating a silicon diode, you pass a constant current, heat the silicon diode, measure the forward voltage. For a constant current, forward voltage will come down 2 millivolts for every degree rise. We use it for measuring temperature coefficient of the resistance of copper. We have a copper coil about 12.5 ohms resistance. You pass a current of 10 milliamperes. It will give you 125 millivolts. So, as the temperature changes, the resistance will increase. From 12.5 ohms, it may go to 15 ohms, 16 ohms, but current will remain constant. So you measure only the voltage difference across the copper coil that will be proportional to resistance. So these are the experiments in which we use the constant current source. It has two ranges. In the lower range, the current will remain constant to 1 part in 10 power 3 up to as the load increases, the voltage across the load will increase. When the voltage reaches 20 volts, up to that, current will be regulated. If you go beyond, if the load increases beyond that value, then the current will not be regulated. There are many experiments in which you use the signal generator or function generator. I don't call it a function generator because we are going to use only sine wave and not triangular wave and square wave. A function generator, my equipment also will produce triangular waves and square waves. It can also be called function generator, but I use it only with sine wave and therefore I call it a signal generator. You can build a signal generator using analog chips, which are relatively cheap and which you can buy in the market. You can make an oscillator which gives sine wave in the RF region using a Hartley circuit with an inductance and a capacitor. This will have an oscillating frequency 1 by 2 pi square root of LC. So if you choose L, a few millihenry, C, 0.1 microfarad, 1 microfarad, you will find frequency will be in the RF range, megahertz, hundreds of kilohertz. It will give pure sine wave. But this type of oscillator cannot give any other form of the wave, triangular or square. And secondly, you cannot use it over a very large frequency region. Whereas a function generator works from a frequency as low as 0.1 Hz to a frequency as high as 1 megahertz or 10 megahertz. So your function generator will give you a very wide range of frequency variation. It will give you different waveforms which you cannot build with a Hartley oscillator. So the function generator uses what is called a relaxation oscillator. In this, okay, there are many chips which are available. You go to Google and you ask for function generator chip. There are many companies which are making function generator chip with different characteristics. One of the most commonly used chip is the chip XR2206. The circuit in this chip has been built by experts, but you can explain how the chip works by considering it as made up of 4 modules. There is the voltage controlled oscillator. There is the current switch. There is the multiplier and sine wave shaper. And there is a buffer amplifier 1:1. The buffer will give a high impedance at the input, low impedance at the output. Same voltage will appear at the output, but impedance will be low. I will explain what each one of these modules does. I think some things have come one on top of the other, but this chip, as you can see, has 3 output terminals. There are 3 other terminals. One to supply the voltage for the chip B.Sc, which may be plus 50 volts, at ground. The other is a bias which you can apply for some purposes. The voltage controlled oscillator has 2 terminals to which you connect a timing capacitor. I will explain what the timing capacitor will do. Then you have 3 terminals attached to the current switch. You will have 2 timing, you can put 2 timing resistors at these 2 terminals, and you can change the frequency from one value to another value by using this FSK terminal. We won't use it, we will get at any one time one frequency output. But suppose you want to work at 100 Hertz and 10 kilohertz by using the FSK and putting 2 resistances here, timing resistors, you will be able to change the frequency at the press of a button. From 100 Hertz, you can change it to 10 kilohertz. But we won't use that operation. Thus, you have symmetry adjustment, where you will adjust the sine wave to have very low distortion by using the symmetry adjust terminals, and you have wave amplitude terminals at 1 and 3. The voltage controlled oscillator will produce an output waveform with a frequency which is controlled by voltage that you apply. The output controlled waveform that we will generate will be a triangular waveform. The frequency will be controlled by the voltage you apply to the voltage controlled oscillator, but the waveform we will get will be a triangular waveform. Now this triangular waveform is generated by connecting a timing capacitor between the terminals 5 and 6. Suppose I put a capacitor C and I put a resistance between 7 and 8, which has a value R, capacitance has a value C, then the frequency of the waveform I will get will be 1 by CR. CR, as you can see, is the time constant for C and R. 1 by CR will be the frequency I will get. Waveform will be a triangular waveform. I can change R by using a pot, keeping C constant, which means I will be able to change the frequency over a certain rate, not over the entire range from 0.1 Hz to 1 megahertz, but I can change it by a factor of 10 Hz to 100 Hz. I can choose a pot with a fixed capacitor. I change the pot, I can change the frequency from 10 Hz to 100 Hz. To go from 100 to 1000 Hz, I change the capacitance to 1/10 of its original value. Using the same pot, I can now change the frequency from 100 to 1000 Hz. So you can have many ranges to go from 10 Hz to, let us say, 100 kilohertz. So 10 Hz to 100 Hz, you will use one capacitor. 100 to 1000 Hz, you will use another capacitor, which is 1/10, the value of the previous one. 100 to 1000, you will use a third capacitor, which will again be reduced 1/10. So you can have a band switch. You can change the choose the capacitor you want and work in the range that you want. Within a given range, you change the frequency by changing the resistance. Now, what does the capacitor, resistance, and the timing switch do? From the supply voltage, it will be applied to the resistance to produce a constant current. So the current will be given by the voltage, supply voltage divided by the resistance that you have attached. So this constant current, when I say supply voltage, you can derive the voltage which produces the constant current source from the supply voltage. It can be 1/10 the supply voltage, 1/5 the supply voltage, and so on. So there is a constant voltage which drives the constant current through the resistance R. You change the resistance, the current will change. Now this current charges the capacitor. So the capacitor voltage will increase at the rate set by the constant current. So the voltage of the capacitor will start increasing when you charge it with a constant current. So it will increase linearly with time. So let us say at time t is 0, it is the capacitor has a voltage Vs by 3. You set the current I, the capacitor voltage will rise at a constant rate till it reaches the value 2 Vs by 3. So this current will charge the capacitor at a constant rate till its voltage reaches 2 Vs/3. There is a comparator in the current switch. This is a flip-flop circuit. What it will do is, it will look at the voltage and the capacitor. When it reaches 2 Vs/3, it will flip and set the current switch. There will be a second current source, but the direction of the current will be opposite to the direction of this current, and it will be minus Y. That means the voltage producing that current will be double the voltage producing this current, and the current will be in opposite direction. So now the total current will be I minus 2I. The current switch will switch on the second current source, so the capacitor will be charged by both the currents. First current is I, second current is minus 2I. So total current will be minus I. So C dV by dt will now become minus I. So the voltage across the capacitor will start decreasing. So when it reaches Vs/3, again the comparator will check the voltage at the capacitor. When it reaches Vs/3, the flip-flop will flip, cut off the second current. So the voltage will now start rising. So you will produce a triangular waveform from the voltage controlled oscillator, the frequency being determined by 1 by Cr. This triangular output you will be able to get out from the voltage controlled oscillator at this terminal. So this is a 16-pin chip, and in this 16-pin chip you have the timing capacitor connected between 5 and 6. You have the timing resistor, the frequency adjusting port connected between 7 and 8, and then your output will come here. You have a switch between 14 and 13. So the output will come at the terminal 13. There is a switch at the terminal 13. There is a switch at the terminal 13. If this switch is open, then the waveform will come here. If this switch is open, the wave coming out at 14 will be a triangular wave. If the switch S1 is closed, you introduce an additional 200 ohms, but there is a wave shaping. There is a wave shaper, sine wave shaper. This sine wave shaper is a diode circuit inside the chip, whose impedance will increase as the amplitude of the triangular wave increases. So the output will decrease as the amplitude increases. So this linear shape will now become a shape like this. So this will shape the triangular wave so that the output becomes a sine wave. It is a non-linear impedance. The impedance increases with the amplitude. So as the triangular wave builds up, the impedance increases, so the output will come down. So you will see that this triangular wave will become a wave which are the rounded near the top, and the circuit components are so adjusted that the output wave that you get when you have the sine wave shaper has a very low distortion from the sine wave. It's about 0.2% distortion. So to get the sine wave, you will have to put this switch down here. You will have to put that. I think I'm too fast for this. I'll change it. So when you put this switch down, then the output you get here will be a sine wave. When the switch is open, the output you get will be a triangular wave. The amplitude of the triangular wave and the amplitude of the sine wave can be changed. So you can adjust the sine wave amplitude anywhere between 0 to 10 volts. The peak amplitude will be 10 volts. Peak to peak amplitude will be 20 volts. The RMS value for 10 volts peak amplitude is 7.07 volts. So you will get an RMS output of 7.07 volts, and this amplitude can be adjusted using a pot. So as you turn the pot, you can increase the amplitude continuously from 0 up to a maximum of 7 volts RMS at all frequencies. Okay? The frequency is adjusted by adjusting this pot here. By adjusting this pot, you can adjust the frequency over the range of factor of 10 to 100 Hertz, 100 to 1000 Hertz. For a given timing capacitor, frequency can be varied by a factor of 10. Now in our signal generator, there is a panel meter. On the panel meter, you have a rough indication of the frequency. Why do I say rough? Rough because the frequency is correct only to within 10%, that indication. My signal generator frequency will be very stable to the second decimal place. But my frequency indication, which involves additional 555 timer circuits, will give you the frequency only for 10%. So where you want to measure the frequency exactly, you use a frequency meter to measure the frequency. Don't take the frequency from the panel meter. There is a DP/DT switch. If you put this switch down, it will, the panel meter will show the RMS amplitude of the output voltage. This RMS amplitude will be correct to within 1 or 2%. So for most experiment, you can take the RMS amplitude directly from my panel meter, but where frequency is important. For example, there are some experiments where you have to measure the frequency correctly. Then you use a frequency meter to measure the frequency. This will also give a square wave because the flip-flop will give you a square wave of a fixed amplitude. So the square wave that you get, that will be the output for the square wave at terminal 11, and this output will be a square wave of 5 volts. It is not a square wave with an adjustable amplitude or duty cycle. It is a square wave which will give you 5 volts output for 50% of the period. The duty cycle will be 50%. You can't change the duty cycle here. For example, you can't change it so that it gives 5 volts for 30% of the time and 0 volts for 70% of the time. You can't change the duty cycle. It will give 5 volts for 50% of the time, 0 volts for 50% of the time. There is a very cheap signal generator that we have built, but good enough. As I told you, I don't know electronics. Many of you may know electronics much more than I do because I never studied electronics. My specialization in research was low temperature physics. Prior to that, I worked in theoretical physics for 10 years, then changed to low temperature physics experiments. But when I was asked to develop this course, I realized I must build some low-cost circuits. So I took a book on electronics, not a book which gives you a lot of theoretical derivation, but a book which gives you how to do things practically. And then I have built all these circuits, trial and error, but all of them work as you will see. My one contention is you must teach electronics in the lab. Ask the students to make 3 projects in one semester. Put 3 students together, ask them to build adjustable power supply, which will give you 2 amperes go up to 30 volts. Ask somebody else to build a signal generator. The student will have to find what type of chips he has to get, what circuit he has to make. He will learn soldering, how to test it. This is how I learned electronics. Some electronics. If you ask me detailed questions, I won't be able to answer. But you will see all these circuits I have built work very well. So a signal generator will give you sine waves in a wide range of frequencies. But you can't draw power from the signal generator. I cannot connect the signal generator to a loudspeaker. I cannot produce 1 kilohertz connected to a loudspeaker because it cannot deliver power. It can deliver 1 milliwatt power. So if your resistance is very high, you can get a small current through that, but it will not give a large power output. So you want a power output of 1 watt, 10 watts to drive a loudspeaker or an electromagnet. Then you will have to use a power amplifier. The signal generator output will be fed as input to the power amplifier. The power amplifier will deliver an output at the same frequency, same waveform, depending on the type of power amplifier you use, but it will deliver a lot of power. You can get 1 watt, 10 watts power out of that. Power amplifier there are again many power amplifier chips. One of the see, when I talk about a chip here, it doesn't mean that is the chip I am using in manufacture. I am talking about some commonly available chips which one can do. The chip that I show here is a very common chip which can be used to obtain a power output of 1 watt. Maximum power output will be 1 watt with a gain of 20. That means you give an input of 10 millivolts, 20 gain means the output will be 200 millivolts at the same frequency, and the power you can draw, maximum power is 1 watt. But you can increase the gain up to 200. This is a very common chip, low cost chip which you can buy, and this chip is LM386. It is an 8-pin chip. If you want to increase the gain, there is an inbuilt gain of 20, but you want to increase it to 200, then you can add some additional capacitance and resistance to the terminal 1 and 8. If you are satisfied with the gain of 20, these two terminals are not connected. You don't connect anything to the two terminals. The input from the signal generator goes between 2 and 3, and the ground is 4. The output from the power amplifier comes at 5. 6 is the supply voltage that you give, and this is a bypass, which we don't lose. Okay. So in this power amplifier, the power amplifier I use will give an output of up to 10 watts in a matched load of 8 ohms. Now all power amplifiers can be classified into Class A, Class B, Class C. Class AB is in between Class A and Class B. In Class A power amplifier, Class A power amplifier, you bias, you give a DC bias. You give a DC bias which is 50% of the supply voltage. This is the supply voltage. This is the DC bias. So when you apply an input, the output can vary from the DC bias up to the supply voltage. It will go from 0 to Vs when the DC bias is 50% of Vs. Because your input is positive sometimes, so the output is positive, input becomes negative, output goes below the DC bias, but because you have biased it up to 50%, output will go down to 0. So you will be able to, because you have applied a DC bias to the power transistor, it will, even when you don't apply an input, it will draw DC power from your supply. So there is a DC power that is being used. This is a drain of the power supply, and this is the AC power it will give. AC output power. This is called the efficiency of the Class A amplifier. How much output power, what is the fraction of the DC input power that you can get as the maximum AC output power. Now this will be 25% for a Class A amplifier. If you use transformer coupling, you can increase it to 50%. But a Class A amplifier will not, the efficiency is pretty low. But there is no distortion because the full signal comes out. In a Class B amplifier, your DC bias is 0. It is a transistor your DC bias is 0. And if the voltage applied to the base goes below 0, there will be no collector current. So the collector current will flow only during the positive half of your input signal. When the input signal becomes negative, the voltage at the bias of the transistor becomes negative, so collector current becomes 0. So you will find that the output will be like this. Only the output will only consist of the positive part of the input. The negative part will not appear. So this will give a big distortion. Because the input may be a pure sine wave, output is not a pure sine wave. It will have a sine wave component, a DC component, sine wave component at the frequency omega, 2 omega, 3 omega, and so on. If you want to avoid this distortion, use class B in push-pull. You have two class B amplifiers. The first one will give out the positive half, second one will give out only the negative half. If you combine the two, you will get the full waveform. Then distortion will be reduced. But because your DC bias is low, the DC input power is low. The output power increases because output amplitude can go up to Vs. So the maximum efficiency of a class B amplifier will be 75%. In class C amplifiers, which are used only with RF, your bias actually becomes negative, therefore you will not even get the full waveform, you will get only, not even for half the cycle. You will get the output for less than half the cycle. This is not used in power amplifier in the audio frequency range. It is used only in the RF range, cell phones, etc., which use RF, then it is used only there. So the power amplifier that one normally uses will be class A, class B, or class AB, where you bias not at 50% or 0, but somewhere in between. So why power amplifier will have an input which will be connected to the output of the signal generator. Output of the power amplifier can be connected to a loudspeaker, or in my case, I will connect it to an electromagnet. So I generate an oscillating magnetic field. This electromagnet may draw a current 0.5 amperes to 1 ampere at a voltage 2 volts, 3 volts. So I get power output of the order of 1 watt or slightly more than 1 watt. But it can give the maximum output of 10 watts in a matched load. You see, the impedance, suppose you use a loudspeaker. The impedance of the loudspeaker, if it matches the impedance of the output impedance of the amplifier, maximum power will be delivered. But this may not happen. Your loudspeaker may have some resistance or some inductance which may have some impedance which may not match the impedance. You use a transformer will reduce or increase the impedance depending on the turns ratio. So you can match the impedance of the loudspeaker to the impedance of your power amplifier by coupling the loudspeaker to the power amplifier through a suitable transformer. I don't do that. What I do here is to match the power. See, I have a copper coil and I have an iron rod. So this is an electromagnet. So the copper coil has a very low resistance. So what I do is to match the impedance, I connect a nichrome wire of nichrome has high resistance, nichrome wire to match up the difference in resistance. This also helps me because my power amplifier is supposed to give an output between 70 Hz to 30 kHz. If you go below 30 Hz, the output will drop sharply. So, in my experiments, the resonant frequency sometimes is 12 Hz. My signal generator will give 12 Hz, but I couple it to the amplifier, power amplifier, it will not deliver enough power to drive my electromagnet. I have to increase the signal generator amplitude. To know whether power is coming here, all I have to do is I touch this micro wire. If it gets hot, then I know my output amplifier is delivering power. If it is not getting hot, I have to increase the amplitude of the signal generator. So there is a very simple way of matching the impedance. It also tells you whether your power amplifier is delivering an output at 12 Hz, 13 Hz, and so on. Now I will start on 12:30. The experiments where we use the signal generator are the following. The signal generator is used in the following experiment. You will measure the impedance of a coil as a function of frequency, calculate its inductance. You will measure the phase difference between the current and the voltage in a coil as a function of frequency, and then get the resistance of the coil knowing its inductance. You will measure impedance of capacitor as a function of frequency. Find out what is the capacitor. You will do series resonance circuit, parallel resonance circuit. All the 5 experiments you will do in one lab session. Using a very small box, you can connect it suitably so that you do all the experiments. So that is one. Then you have passive filters. You have a resistance capacitance network so that it acts as a low pass filter or a high pass filter or as a band pass filter. You can measure filter characteristics there. 3. All 3 filters you will do in one session. 3. AC bridges. There are 3 AC bridges, the Maxwell bridge to compare inductances, the De Sauty bridge to compare capacitances, and the Maxwell bridge. One arm is an inductance, one arm is a capacitance. You will do all 3 AC bridges in one session using the signal generator. Levi's law in ferroelectric. So I have a ceramic capacitance. It contains a ferroelectric material with a Curie temperature around 20 degrees centigrade. So above 20, the material is paraelectric. You can measure the capacitor as a function of temperature. To measure the capacitor, I use a fixed frequency. I connect a resistor in series with the capacitor. To measure the voltage across the resistor, voltage across the capacitor, the ratio gives you impedance of the capacitor by 1 kilo resistor. So you know the impedance, you know the frequency, so you can calculate the capacitance. You plot 1 by C again temperature, you will get a straight line, you will verify 2Levi's law. 5. Thermal relaxation of a serial bulb. I have a 5 volt serial light bulb. Through this I will pass a DC current, fixed value. Superposed on this I will pass an AC current, fixed current, but frequency varying from 20 to 100 Hz. So the bulb will flicker in intensity. This light will be picked up by a photodiode. Photodiode will give an AC output, and as you increase the frequency, the AC output will come down. You can measure the relaxation curve. Maximally device relaxation. You can measure using this. Then lock-in amplifier. I have got a lock-in amplifier which will work between 100 Hz to 5 kilohertz. It will amplify AC voltages, microvolts, 5 microvolts, 10 microvolts, give output in millivolts. You can see how body phase sensitive detection on the oscilloscope. You can calibrate the lock-in at different frequencies, and you can use it for measuring mutual inductance of 100 microhenry. I will verify all laws of mutual inductance with a maximum current of 800 microamperes. That is the power of the lock-in. Current is very low and the mutual inductance is very low, but I can still measure the mutual inductance to an accuracy of 1 or 2%. And probably, okay, these are the 6 experiments. And then there are 2 more. Young's modulus of a brass bar and a rigidity modulus of a wire. I will find the resonance frequency of the brass bar by adjusting the frequency of the current going through the electromagnet. I will find that top frequency, you get the maximum amplitude. So I will measure the resonance frequency. I will show that the hormone in the second mode, second higher frequency mode, is 6.22 times the fundamental mode. Because the differential equation for flexural vibration is 4th order in space, 2nd order in time. Frequency will vary as 1 by L square, flex square as a bar. You will verify it, and you will also verify that if the fundamental frequency is 20 Hz, the next higher frequency of vibration is 20 into 6.22. Then you can do rigidity modulus. You do the rigidity modulus by having a long wire with a weight. You twist it, you look at the light spot, and you measure the period. Here I have a tabletop model. The wire is stretched between 2 points. At the center you have a brass disc, which is the moment of inertia, with 2 prongs and 2 magnets. There are 2 electromagnets, this will push this magnet back and and this will push this magnet back. So it will apply a torque, and I adjust the frequency to get maximum amplitude. You will verify frequency is proportional to 1 by square root of L. Ln. If you want, you can put another characteristic S0 to increase the moment of inertia. You can verify it is proportional to 1 by square root of moment of inertia, and you can calculate the exponent. These are the experiments where we will use the signal generator, and in these two experiments I will use the power amplifier along with the signal generator. You can make a Kutz tube experiment. Put a loudspeaker, put a piston which can be moved, find the static wave, then you can measure sound velocity in air. You can drive the loudspeaker using my power amplifier. 1 kilohertz frequency you can use, and you can drive the loudspeaker at 1 kilohertz using the power amplifier. So these are the different experiments where we will use a signal generator and a power amplifier. So that finishes what I have to say. See, this time I am having some problems. Problems are, one of the resource persons dropped out last week, so I have to redistribute the lectures. And then this morning I got an email, another resource person has some medical problem, she has to undergo some scan. If things are okay, she will come tomorrow. If she has to undergo any surgery, she will also drop out. But it doesn't matter, because I can give lectures on all the topics. Because I have set up the experiment, I can do that. But the number of resource persons available will become less. So in the lab, 2 people will have to wait. Secondly, I'm supposed to get a new kit from Bangalore, which was dispatched on 1st July. It has not arrived so far, but I'm using some of the old equipment which has come from Rajahmundry. But in transit, some of them have gone bad. I have not repaired it so long, because every time I get a new kit, I use it. This time I have not got it, so I have to repair whatever has gone bad and use it. I have set up 8 experiments. The remaining 9 experiments I hope to set up today when I am free, tomorrow when I am free. And I will check all the experiments, and you will have no problem in doing all the experiments. The manual, I told them to print out and give it to you so that you can see how to make the calculation. If you get a CD, then you will have to put it on a computer to read. So I request